There is a knife in your kitchen drawer, and it is better than almost anything a medieval smith could have made. That is not flattery aimed at you. It is just true. The stainless steel in a cheap modern blade is more consistent, more corrosion-resistant, and more precisely controlled than nearly anything available before the 20th century. Someone measured the carbon in it to a fraction of a percent. Someone knew exactly what temperature it was at, the whole way through. So when you hear about a legendary lost sword-making technique, your instinct is probably to file it under romance. Old things get exaggerated. Swords get poems written about them. Nobody in the 12th century was outperforming a modern factory. That instinct is right about almost everything. It is wrong about this one. The real answer is far stranger. When researchers finally put a genuine blade of this kind under an electron microscope, they found structures inside the metal that nobody could even name until the 1990s, and the recipe that produced them was lost so completely that we still cannot reliably reproduce it. The blades are usually called Damascus steel, which is slightly misleading, so decode that first. The name attaches to swords traded through Damascus, but the steel itself came from somewhere else. It was made in South Asia and Sri Lanka, and shipped west as small cakes of raw metal. That raw material has its own name, Woots. Woots was made by sealing iron together with carbon-rich material, plant matter, leaves, wood, in a closed clay crucible and holding it at high heat for a long time. Long enough for the iron to absorb far more carbon than a European bloomery furnace could manage. What came out was an ingot of very high-carbon steel. Then a smith forged that ingot into a blade, and the finished blade carried a surface pattern of flowing, banded, watery lines that nobody could fake and nobody could quite explain. Now here is where the reputation comes from, and it is worth being careful because this is where the internet usually starts inventing things. The historical claims about these blades cutting through European swords or slicing a falling silk scarf in mid-air are legend. Treat them as legend. What is documented is more modest and more interesting. Crusader-era accounts describe the steel as unusually hard and unusually tough at the same time, which in metallurgy is close to a contradiction. Hard steel is normally brittle, tough steel is normally soft. Getting both is the whole problem, and it still is. So the real question is not whether the swords were magic, it is what was physically going on inside that metal. Answering that took equipment that did not exist. For most of the time, people were arguing about it. In 2006, a team at the Technical University of Dresden, led by Peter Porfler, took a genuine 17th century Woots blade, dissolved away part of the surface with acid, and put what remained under a high-resolution transmission electron microscope. That is an instrument that fires electrons through an extremely thin sample and lets you see structures at the scale of individual atoms. What they reported was carbon nanotubes. Decode that immediately, because it sounds like science fiction, and it is not. A carbon nanotube is a sheet of carbon atoms rolled into a cylinder, so small that you would line up tens of thousands of them across the width of a human hair. They were formally identified and named in the early 1990s, and they are one of the strongest materials known. And Porfler's team reported finding them along with nanowires of cementite, an iron-carbon compound apparently encased within the tubes. Sit with the timeline for a second. A material that modern science identified in the 1990s, sitting inside a blade forged in the 1600s from a recipe that is older still. Now, the honest part, and this matters more here than in most of these stories, that finding is contested. It has been since it was published. Some metallurgists question whether the nanotubes were genuinely part of the original structure or an artifact of the preparation, whether the sample was representative, and whether nanotubes explain any of the blade's actual performance, even if they are there. There is broader agreement on the banded cementite structure and on the role of trace elements, and much less agreement about the nanotubes specifically. So do not walk away saying medieval smiths engineered nanotechnology. They did not. Nobody was aiming at a molecule. What they were doing is stranger than that. They were following a procedure, handed down and refined over centuries, that happened to produce structures at a scale nobody involved could have imagined, let alone observed. and the trace elements are where it gets genuinely uncomfortable. Work by John Verhoeven and Alfred Pendray, an academic metallurgist and a working blacksmith who spent years collaborating on this, found that reproducing the surface pattern depended on tiny quantities of certain impurities in the ore, vanadium in particular, not added deliberately, present in the specific ore deposits that the original steel came from, in quantities measured in fractions of a percent, which gives you a mechanism for the disappearance, and it is bleaker than any story about a guarded secret. The usual explanation is that the technique was hoarded by master smiths and died with them. That may be part of it, but if the effect depended on the chemistry of particular ore beds, then when those specific deposits ran out or shifted, the recipe simply stopped working. The smiths would have kept doing exactly what they had always done, and the pattern would have stopped appearing, and nobody would have known why. Imagine that. You are following your master's instructions precisely. The steel is coming out wrong. You cannot see the reason because the reason is an element you have no concept of, present in a quantity you have no way to measure. So here is the twist, and it is not about swords at all. That knowledge was never written down as knowledge. It was carried as procedure. Do this, at this heat, for this long, with metal from this place. It worked for centuries, and the people using it could not have told you why, because the why was buried at a scale no human eye would reach for another 1,000 years. And when the conditions quietly changed underneath it, the whole tradition had no way to adapt, because you cannot troubleshoot a variable you do not know exists. Which is the part worth carrying out of this. Think about how much of what works in your own life you have never actually examined. The routine that keeps your week functional. The way you handle a difficult person at work. The thing you do before you sleep that means you sleep well. You did not derive any of it. You copied it or stumbled into it, and it worked, so you kept it. You are running procedures whose mechanisms you have never inspected. Most of them are fine. But some of them depend on a condition you have not noticed, and when that condition changes, the procedure will stop working and you will not know why. You will just be doing the same thing you always did, wondering why the results went wrong. There is a knife in your kitchen drawer, and it is better than almost anything a medieval smith could have made. But nobody knows how to make what he made, and neither did he.